Ask an AI a complex question, and it responds with a flawlessly structured, highly confident answer. The grammar is perfect, the tone is authoritative, and every single fact in it is completely wrong. To fix these errors, engineers rely on a field called mechanistic interpretability. They slice open the black box to map the static neural circuits and trace how specific inputs lead to specific outputs. But mapping the static anatomy of a network has a hard limit. If you map the physical anatomy of a human brain, you gain valuable structural information, but that map will not tell you if the patient is currently experiencing a panic attack. Knowing how an artificial intelligence is built mathematically does not reveal what it is experiencing computationally during the exact dynamic moment it fails. Researcher Joshua Duran proposed a new scientific discipline to bridge this gap: machine psychology. Instead of charting static anatomy, this framework reads the real-time physiology of an operating AI model. To be clear, this framework does not claim that machines possess human emotion, sentience, or consciousness. Researchers are instead measuring what they call machine-native inner states. These are measurable computational dynamics that functionally behave like tension, hesitation, or confidence, entirely driven by math. Shifting our focus from static maps to dynamic monitoring exposes a highly active environment inside the black box, a constant flux of computational cognitive weather. This diagnostic framework operates like a non-invasive EKG. It passively measures internal signals without altering a single line of its underlying code or weights. Layer 1 extracts raw data, tracking granular metrics like entropy gradients and attention weights in real time. Layer 2 monitors how those signals interact, scanning for computational drift. Layer 3 translates these mathematical patterns into a taxonomy of cognitive weather, bracketing the chaos to classify it. One of those classifications is agitation. When the system shows high internal conflict and low computational stability, the model is agitated. Another is saturation. This occurs when the system's context window is completely overloaded and reaches its absolute representational limits. By stacking these observational layers, researchers convert raw, chaotic data points into a readable moment-to-moment diagnosis of the AI's operational health. This raises an immediate question: is this a specific quirk or a universal phenomenon? To find out, researchers ran an empirical test known as T10. They compared a standard language model against a distinct model trained exclusively for formal mathematical proof generation. Despite fundamentally different training data and operational purposes, both models exhibited the exact same structural geometry when placed under identical internal stress. This is a homologous NR architecture. These states aren't quirks of training, but mathematical invariants appearing whenever these networks process information. Because these machine-native states transcend specific programming, machine psychology operates as a transferable science of artificial logic. We can now return to the problem of the highly confident hallucinating AI. The T08 empirical test was designed specifically to determine if internal structural pathologies actually precede these failed outputs. This chart tracks a pathology discovered during the test, the hallucination mirage. It happens when an AI commits to an incorrect pathway with brittle certainty. The system's entropy collapses, masking internal conflict and generating false certainty steps before the wrong word is ever generated. This hidden pathology causes the model to output a confidently wrong answer, leaving the end user completely blind to the internal breakdown that just occurred. A hallucinated text output is merely a lagging indicator of a computational disease that began much earlier in the generative process. This discovery moves AI safety away from post-generation content filters and toward real-time internal state monitoring. Operationally, a system experiencing severe agitation or a hallucination mirage could automatically trigger human review or simply halt its own generation before it ever speaks. We stop treating these systems as opaque text generators and start interacting with them as transparent cognitive engines. By reading the physiological pulse of the machine, we can finally catch the system failing before it ever has the chance to tell a lie.